Hi there, my name is Charles Msipa. Welcome to another presentation on complex functions. In particular, we are going to discuss the computation of residues. Now, we start this way. We're given an example which says determine the residues of a complex function f of z equals to z over, in brackets, z squared plus 1 multiplied by 3z minus 1 at each of its poles on the z plane. Now, it is important to first of all know exactly what you mean by a pole or poles of a rational function like f of z. And then, so as solution, reflecting on that, this is solution. It has to be clear to all of us that when we're talking about poles, we're talking about the point of singularity. In this case, recall relating this to Lorentz series, that at a pole, the Lorentz series will have a finite number of terms in its principal part, and the poles, let's say poles, we know that poles occur where the denominator of the rational function is equal to 0. Now the denominator, let's say d z is equal to 0. Now for a rational function like this one, f of z, we'll consider this f of z is made of two polynomials of z, which is the numerator n z over d z. So in order to determine the poles, we need to set an equation of this form which says dz is equal to 0. In this particular case, we've got z squared plus 1 multiplied by 3 z minus 1. Setting this equal to 0 and solving this equation will identify us. We'll be able to identify our poles. In this case, we know that this would mean that 3z minus 1 is equal to 0, whereby we get that z is equals to 1 over 3, dividing both sides by 3. And on the other hand, we've got z squared plus 1 equals to 0. And we know that this can be factorized in a set of complex numbers as z minus I multiplied by z plus I. If you've gotten this, please try to revise your operations with complex numbers and see that this actually gives you this kind of expression. So therefore here we're going to have z equals to I or z equals to minus I. In other words, our poles, set of our poles in this case will be I minus I and and 1 over 3. We're not going to require that you write this exactly this way. I'm just making it very, very clear here that after setting a limit equal to 0, you need to be able to identify your poles to be 3 poles, which are I minus I and that. In this case now, we can rewrite our function f of z equals to z over z squared plus 1 multiplied by 3z minus 1. You can rewrite this as z over z minus I multiplied by z plus I multiplied by z minus 1/3 In this case, we're expressing this function with its denominator factorized fully and being able to see each of the poles we identified here. I hope you can see that in this factor 3z minus 1, we're able to take a common factor 3, dividing by 3 in brackets, we got here z minus 1 over 3, which you wrote here as z minus 1 over 3 multiplied by 3. So now we're able now to see that we've got 3, in this case 3 simple poles. Now for this, we need to now recall our formula for computing simple poles. Now we see we're going to be able to also calculate the 3 residues. Now it's 1 residue per pole. Starting with residue at z equals to 1/3, we'll try it now and say residue of f of z at z0 equals to 1/3, and this is a simple pole. We'll then close there and say this is equals to, according to our previous discussion, so that this is equals to limit as z is approaching 1/3 limit of the expression of this form, z minus 1/3 multiplied by the function f of z. So what we do here, we first of all take the function f of z multiplied by that, then followed by computing a limit. Now doing this calculation on the side, we'll take f of z, which is z equals to z minus I z plus I and z minus 1 over 3 multiplied by 3 here. If we then multiply this by z minus 1 over 3, in other words, you have got f of z multiplied by z minus 1 over 3. We can clearly see that this factor and this, they simplify to 1, then we're left with z over 3 times z minus I multiplied by z plus I. So computing limit here, this will give us limit as z is approaching 1/3. That will be limit of z over 3 z minus I multiplied by z plus I. Now, if you recall your theory on computation of limits, you can see here that this function is actually defined at z equals to 1/3. And you recall that if you put let's say a polynomial pz, which is a nice function which is defined everywhere. Now, if you want to calculate the limit of p of z and the z approaching a, this limit will be simply equals to the value of the polynomial at a. So this similar situation also happens if we're dealing with rational functions, and the point at which we're upward computing limit, the rational function is defined. So we can just plug in the value of the point at which we'll calculate the limit in the expression of the rational function and then get the limit. In this case, equals to 1/3 over 3 brackets 1/3 minus I brackets 1/3 plus I. Now our next step will be to simplify this expression and write it in a more compact way. In this case, using the difference of two squares here, this would give us will be 1/3 over 3 brackets 1/3 squared minus I squared. We all know that I squared will give us -1. Then you're going to have minus 1/9 minus -1 will be +1. Then we're going to have 1/3 over 3 brackets 1/9. You're going to have 1, which is simply 9/9. And the simplifying there, we're going to have 1. Simplifying this, the 1/3 over 3, we're going to have 1/3 times 3 multiplied by 9 plus 1/9, which is 10/9. And this simplifies to 1/9 multiplied by 9/10, which would give our residue to be 1/10. That would be how we calculate the residue at the point given. Now proceeding now to the next pole. Our next pole is, let's take minus I we have a function f of z as z over 3 brackets z minus I multiplied by z plus I multiplied by z minus 1/3. Now we need the residue at z0 equals to I. So in this case, this tells us that we need to multiply our function by z minus I. So multiplying this, let's first of all state here that residue of f of z at z equals to I. Again, this is a simple pole. This will be equals to the limit at z is approaching I, the limit of z minus I multiplied by f of z. Now, at this stage, now we're going to move a bit quickly. Now we can see that if we take this vector and multiply here, this vector and this same vector on the denominator will simplify to 1. Then our expression here will calculate the limit. We're going to remain as z over 3 times 3 plus z times z minus 3, which you then write here as the limit as z is approaching I of z over 3 multiplied by z plus 1 multiplied by z minus 1 over 3. So this is after multiplying f of z by that vector. Now again, we can see that this expression has no problem being undefined at z equals to I. So now we can compute the limit by simply plugging in this I into the expression and then simplify, which will give us I over 3 brackets I plus 1 multiplied by I minus 1 over 3. Sorry, there's a mistake in this expression here. This is not I, this is not 1, this is I. And then this is also supposed to be I. So, because the factors here is z plus I, not z plus 1. Okay, having that mistake corrected, this will simplify to I over 3 multiplied by 2I in brackets I minus 1 over 3. 2I from I plus I multiplied by 3. Then simplifying this expression, you can see that this I and this one simplify to 1. Then we've got our final answer being 1 over minus 2 from multiplying 6 by minus 1/3 plus 6I. So that will be our residue. Now, if we want to express this in rectangular form, remember we need to multiply this by 1 written in terms of the conjugate of the denominator. In other words, we multiply here by minus 2 minus 6I over minus 2 minus 6I. And then this will take us to, migrate us to the form of a complex number, which is A plus IB. So you can simplify that for yourself. Now, the last residue which we need to calculate here is the residue at z equals to minus I. Then computing residue at z equals minus I, let's write residue of f of z, z0 equals to minus I, and then we'll write this as limit as z is approaching minus I. In this case now z, the factor you're going to use, we're going to multiply by z minus I, which gives us z plus I, multiplying f of z. Then after multiplying here, we compute the limit. So I'll leave this one for you and label it here. Do it yourself. Just show that you can repeat the steps done just above and compute the residue. Otherwise, up to this point, thank you for listening.